In this lecture, I'm going to cover the topic of sampling and reconstruction. So we're going to study more in detail what I introduced in the first lecture about sampling and reconstruction. And I have to say that this probably is going to be the most difficult lecture, one of the most difficult lectures of the course. At first, it will not be clear what we are doing. However, if you put the effort of studying this lecture, you will actually in the end understand that this is not as difficult as it may seem at the beginning. So let's look at the slide. So what we have is that discrete time systems and continuous time systems are interconnected by means of samplers and holders. So the samplers are those devices that convert our continuous time signal to discrete time. So they are an analog to digital converter. And the holders are those devices that convert our discrete time signal to continuous time signal. So they are digital to analog converters. So what we try to do in this lecture is trying to describe what happened when we use this device, what happened to our signal from a mathematical point of view. The sampler converts a continuous time signal into a sequence of samples taken at the sampling times, where the sampling time is capital T. We have to remember that the only information that we have is at the sampling time. So it means that when we reconstruct our signal, the reconstructed signal may be very different from the original signal. And the reason is that we don't have information between sampling times. So the main reason, obviously, that for us to actually want to convert a continuous time signal to a discrete time signal and introduce approximations is actually that we have a benefit. And the benefit is that we can process this with a microcontroller. And I explained in the first lecture what are the advantages of a digital control system with respect to an analog control system. So the basic scheme that we have is that we have our processor that takes discrete time signals. So we have to sample our continuous time signal. The processor will give us a discrete time signal, and then we have to reconstruct the discrete time signal using an old device. So let's study the simplest possible configuration. And the simple possible configuration is the cascade of a sampler and a hold. So what we do here is just taking a signal, sampling the signal, and then reconstructing the signal. So this is the simplest operation. And we want to see what happened and how we can describe, in particular, this signal. So the first part of this lecture will focus on finding a mathematical description for this interconnection. A mathematical description that put in relation the reconstructed signal with the original signal. The device that we use will be a zero-order hold. And a zero-order hold is a device that takes the sample and keeps the output equal to that value for all the times between kt and k plus 1 times t. So this basically is saying that the whole device keep constant the signal. So we already saw in this device in the first lecture. This is the simplest possible hold, and we will study more complicated holds. However, for this analysis, we can keep it simple and we use this hold. So if we use a similar analysis can be performed with different holds. So how do we describe mathematical this? So we consider the sequence x of kt, and we assume that the sequence is 0 for negative times. This is a standing assumption for all the course. Then the reconstructed signal is given by this expression. Okay, so this is the output of the hold, and this expression is the sum, with k goes from 0 to infinity, of x of kt, that multiplies this function here. So this function is the difference between h at a certain time and the h at another time. Okay, what is h? H is a function that is 0 for negative values of the argument. So when t is less than t0, this is 0. And when t is greater than t0, this is 1. So this is basically the unit step. Okay, so this is the unit step function that from now on we indicate with the letter h. So this is the difference between two steps. So let's try to understand at the board what this means. Okay, so what we are actually doing. So how a hold device works. So this is our time axis, and the reconstructed signal is reconstructed in the following way. So this is x r of t. So the whole device take the first sample, okay, that is x of 0, and then it keeps constant the sample up to the next sampling time. Now we measure the next sample, and for instance we end up over here, and then it keeps constant this up to the next sampling time. So this is x of t, okay? And then again, so let's say that this is x of 2 capital T, okay? And you keep it constant. And let's say that the next value is over here, and then you keep it constant. So this is x of 3 capital T. And then we have this is x of 4 capital T, and so on, okay? And so on. So this is how the reconstructed signal may look like. So you take the sample and you keep it constant up to this next sampling time. So we can describe these using the difference between unit steps. To show this, let's find, okay, let's compute the first term of this sum. So the first term of this sum is x of 0 that multiplies h of t minus h of t minus capital T, okay? So this is the first value, okay? So let's put here h of 0, and let's first sketch h of t. So we sketch h of t with the color blue, okay? So h of t is just the step. So it's this function over here. So this is h of t. And now I sketch minus h of t minus capital T, okay? So this is a function that is 0 when t is less than capital T. So it's 0 here. And then since we have the minus here, it's minus x0, okay? So we go here, and then it's constant like this. So here we have minus x0. So this function is minus h of t minus capital T multiplied x of 0. Also there we have multiplied x of 0. Okay? Now what we do is the sum of these two terms, okay, and we do it in green. And when we do the sum, so 0 times 0 is 0, then 0 times x0 is this guy here, okay, and then we do x0 minus x0, and so we go back here, okay, and this is basically the first term of this sum. So if we report this here, we obtain basically this element over here. Now, it's easy to convince us that if we add the second term of that sum, okay, so if here we add plus x capital T of h of t minus capital T minus h of t minus 2 capital T, then what we will get is will be this other guy over here, and so on, okay? So we convinced ourselves that this expression here is actually a reconstruction using the whole device of the signal, okay? So now let's go on, and let's recall that the Laplace transform of the unit step is given by this expression. Why? Because this is the Laplace transform of the unit step, that is 1 over s, but this is shifted in time, so we have to use the shifting theorem for the Laplace domain. So if you remember the shifting theorem for the Laplace domain, then this corresponds to multiply for an exponential power minus k capital T, okay, s. So this is the Laplace transform of the delayed unit step. So this means that the signal, the reconstructed signal x of r, is Laplace transformable, and we can compute the Laplace transform of this signal. And what we obtain is that the Laplace transform of the reconstructed signal is this sum times, so the sum with k goes from 0 to infinity of x of k capital T times this, this function. Now we see in this function that we can factorize x power minus k ts. So we factorize this out, okay? And what remains is this guy over here. And we notice that this guy does not depend on k, so we can bring it outside the sum, okay? So now we can write this in the following way. So the Laplace transform of the reconstructed signal can be expressed as the product of two functions. h0 of s, that is given by this guy outside the sum, and then a function that we call x star of s, that is given by this expression over here. Okay? So to write this in a clear way, we have that the Laplace transform of the reconstructed signal is equal to h0 of s times h star of s. Okay? So we have written the Laplace transform of the reconstructed signal as the product of two terms. So I recall again, before going on, that our objective is to find a mathematical description of this interconnection. Up to this point, we have found this formula, okay? We still didn't reach the final result, okay? But we reached this interesting description. So let's go on, back to the slides, okay? And we see that x star of s is the Laplace transform of a signal x star of t, which depends only on the sequence of samples x of k capital T. So we see that he has this this expression here where it does not appear x of t, but it's x of kt that appears in this expression, okay? So let's try to understand what this signal is. I want to point out before going on that we call this Laplace transform the starred Laplace transform of x, because there is this star here, okay? And we will see a lot of starred Laplace transform in the course. So let's try to understand what is this x star of s, okay? So x star of s can be, we can compute the inverse Laplace transform of this. So this is the signal that we want to, for which we want to compute the inverse Laplace transform. And we see that when we do this, this term is constant in the S domain. S does not appear. So basically, this is just a constant function, okay? And then we have the exponential. And we remember that exponential in the Laplace domain means shifting in the time domain. So this is basically the shifting of the constant. So it means that the inverse Laplace transform of a constant is a delta Dirac impulse, okay? But since there is the exponential, this is shift, okay? So in other words, the coefficient is constant and stays there when we compute the inverse Laplace transform. The basic function here is basically 1, okay? It's a constant. And the inverse Laplace transform of the constant is a Dirac impulse function, okay? And since we have the exponential, this impulse is shifted by kt. Just to recall what a Dirac impulse is, the Dirac impulse can be represented and can be understood in the following way, okay? It's a function that is described in the following way, in which here we have a base of this function is epsilon, and the height of this function is 1 over epsilon. So the delta of t is defined as this when epsilon goes to 0. So when the base becomes very, very small and the height becomes very, very high, okay? So now we can write this in a more compact way, okay? And in particular, we can define a function delta capital T of t as the sum with k that goes from 0 to infinity of these of all these shifted delta here, okay? And we can we can write the star x of t as x of t times this function here. We can use here x of t instead, so we can basically bring outside xkt and replace it with x of t, because when we multiply a signal for this function, what is this function? This function is a train of impulses, okay? So it is something like this, okay? You see that when we multiply this for whatever function we have, we actually end up only with these values here, okay? Because here it's 0, 0, 0, 0, and 0, okay? And this actually goes up to infinity because it's an impulse. So we can write x star of t as the product of x of t and a train of impulses. So this basically gives us an understanding of what this x star of t is. X star of t is obtained from x of t when we sample x of t, not with a normal sample, but with a sample that is an impulsive sampler, because it's a sample that happens in impulses, so it happens infinitely fast, okay, and produce this x star of t. We have to point out that an impulsive sampler does not exist in real life, okay? We cannot realize in practice an impulsive sampler. So what we obtain here, something that doesn't exist? No, because the impulsive sampler here is just something that makes us understand what is happening, okay? We don't need to build any impulsive sampler, okay? This is just telling us that this x star of t, this signal that appears in the mathematics that maybe we don't understand, is actually what we obtain if there exists an impulsive sampler and we use it on the signal. That's what happens when we use an impulsive sampler. We get this x star of t, okay? Now, we don't have to build any impulsive sampler, okay? So this is just to make understand, to give us a justification, an intuition of this x star of t that we have obtained in this basically slide, okay? So now we summarize what we obtained so far. We obtained that the Laplace transform of the reconstructed signal is actually equal to the product of two functions, okay, where one function is given by this Laplace function, and the other function is x star of s. So x star of s basically can be seen as the input of the transfer function h of 0 of s. And h0 of s basically becomes a correct mathematical description of the whole device, in particular of the zero order whole device. And this is true provided that the sampler, okay, is actually replaced with an impulsive sampler. So this is explained better in the next slide. So we have solved part of our problem, that is how to describe this interconnection. We have found that from an input-output perspective, so it means that if we look at what happened to the output when we give this input, okay, what happened is that this interconnection is actually equivalent to the interconnection of an impulsive sampler and the transfer function h0 of s. So we can describe this interconnection with this other interconnection. What is the difference between this and this? Is that we can write basically this in the Laplace domain. So we have a Laplace version of this interconnection, for which we know that this is h star of s, and we know that this is h0 of s. So we have found that the output, okay, of this interconnection, xr of s, can be written as the product of these two functions, okay? So the next step, you can imagine, will be actually to go then from the Laplace domain to the Z domain. At that point, we have solved our problem of trying to have a mathematical discrete time description of this interconnection. I want to point out that if you take the whole device, so the whole device is a device that keep the signal constant up to the next sampling time, okay? And you compute the Laplace transform of these, you actually get this. So this is not just a random Laplace function that we obtain, but this is the Laplace transform of a zero order whole device. Now, what I said is that our final goal is to actually find a discrete time description of this interconnection. We have the Laplace transform of this. We can compute the Z transform of this Laplace transform. So what we are missing is the Z transform of this block here, and in particular the Z transform of X star of t. But let's look again at X star of S. And this is the expression of X star of S that we have seen a few slides ago. And we see that actually we recognize that this is actually similar to the definition of the Z transform. This is actually the Z transform of the sequence when Z is replaced by e power S capital T. So let's do this replacement. So if Z is equal to e power S capital T, this means that S is equal to 1 over T natural logarithm of Z. So we have just inverted this expression. So now we take X star of S and we replace S with this expression. We get X star of 1 over T logarithm of Z, and this is equal, just replacing, the S over here, to this, and this is actually X of Z. So we see that the X star of S is in one-to-one relation with the Z transform, X of Z. What does it mean one-to-one relation? It means that given one of the two, so for instance X star of S, then X of Z can be determined in a unique way. So for a specific X of star, there exists only a unique X of Z, and vice versa. It means that we can use one or the other without paying too much attention to it, because they are basically a different way to describe the same object. So it means basically that X star of S can actually be just replaced in our mathematical description when we want to go in the Z domain with X of Z. It means that if we have an expression in which all the terms that appear are starred Laplace transforms, we can replace all the starred Laplace transforms with the Z transform. Maybe this is a bit unclear now, but in the next lecture, this will be more clear. This is basically the most important result of this part of this lecture, the fact that X star of S can be replaced by X of Z. Okay? Why we want to do this? Why we want to replace X star of S with X of Z? Because X of Z is actually a better function than X star of S. X star of S is a transcendental function. It's a function in which we have exponentials. Exponential are transcendental functions. And these exponentials are difficult to deal with. Okay? However, the Z transform is actually a rational function. We have studied up to now that the Z transform is a fraction of two polynomials. And we know that we can deal with it very easily. We can implement it at the computer. We can compute the inverse Laplace transform using partial fractions or the inversion integral. If instead of having this, we have to deal with X star of S that is transcendental, then things becomes much more complicated. So there is an advantage in replacing X star of S with X of Z. This concludes the first part of this lecture. As you can see, we have covered the sampling and reconstruction part 1 and part 2 of 5. So part 1 and part 2 are together, and what we have seen is how to describe this interconnection in a mathematical way, and we have seen that this interconnection can be described by this other interconnection. This is a mathematical description, but what is the advantage of this? The advantage of this is that at one point we'll see how to convert this in the Z domain, and what we will have will be just Z transforms. This concludes this part of the lecture, and now we go on other aspects of sampling and reconstruction.